Good morning. Is this thing on? Good morning. Hello, test. 1, 2. Hello? Good morning. Can you hear me? Not a lot of gain on this. Okay, good morning. My name's Jeff Beer. Professor Lee invited me here to present a guest lecture today. Very excited to do it. I graduated from Cal with a master's degree in 1989. It's nice to come back from time to time. Can you hear me in the back? Let's see. Is there an electrical engineer in the house? See if there's a volume control here somewhere. Lamp dimmer. Seriously, does anybody know how to operate this thing? I don't see anything that looks like a volume control. Thanks. Better? Is that okay? Keep going? All right. It's set to 11 now. Can you hear me in the back now? All right. Good morning. My name's Jeff Beer. Professor Lee invited me here to... Is that too loud? It's a little bit too loud, huh? It's loud in my head. I don't like to hear my voice echo like that. Let's try this. Good morning. My name's Jeff Beer. Professor Lee invited me here this morning to present a guest lecture. I'm really happy to be here. I graduated from Cal with a master's degree in 1989. It's nice to be back. Have we already established that none of this material will be on the final? Yeah? Okay, good. So we can be kind of free form and you can ask questions and ask about what you really want to know about without worrying about what you're going to be tested on. I think that's best anyway. So I understand this is a class on embedded systems. Yes? Okay, so this is going to be a presentation about giving sight to embedded systems, or another term for this is embedded vision. This is a perfect time for this presentation because in your careers, I predict if you go into design of embedded systems, vision is going to become one of the most important capabilities of embedded systems over the next 20 years. I have spent about 25 years in industry on various kinds of embedded systems design topics and processors and tools for embedded systems. And if we think about 20 years ago, think about Wi-Fi and wireless networking. If I went to an embedded systems design conference 20 years ago and said, let's say I met a guy designing vending machines, right? And I said, hey, what kind of wireless networking are you putting in your vending machine? I would get a blank stare. What are you smoking? Of course, we're not putting wireless networking in vending machines. That's ridiculously expensive and complicated. Today, if I have that same conversation, it's exactly reversed. If you're not putting wireless networking in your vending machine, you're the one who needs to have your head examined, right? Because it's so easy, it's so cheap, and it provides so much value. Otherwise, how are you going to update the pricing in the vending machine? How are you going to find out when it needs to be restocked, et cetera? Of course, you're going to put wireless networking in because it's virtually free, it's really simple to integrate, and it brings all kinds of added value to the machine. Same is about to be true for what has been known for decades as computer vision. In most fields today, people designing embedded systems, if you have the conversation, hey, what kind of computer vision functionality are you putting into your vending machine? You get that same reaction that Wi-Fi got 20 years ago. Are you crazy? That's a technology like nuclear fusion. Yeah, it's really cool and powerful, but it's just way too complicated and expensive to use here. That has been true for the last 50 years. But it's not true anymore. And the system designers who are being clever about incorporating vision into products today are getting huge gains by doing so. And in 20 years, I think we'll have the same situation that we have now with digital wireless. It's going to be taken for granted. It's going to be ubiquitous. Almost every kind of system is going to have vision because enormous benefits come to systems from having vision. And it's going to be pretty easy and pretty inexpensive to do, just like wireless is today. This quote from neuroscience is very, I think, inspirational in that regard. This is, of course, about human vision. Human vision, depending on which neuroscientist you talk to, takes somewhere between a third and a half, or maybe a little bit more of the human brain. If you think about that in computation terms and evolution terms, I think you can infer two pretty interesting things that also apply to artificial vision, or embedded vision, as I call it. Thing one, it must be hard. Vision must be hard, otherwise why would we need half of our very powerful brains to do it? It must be a computationally hard problem. That's true. Number two, it must be really important. If evolution has decided to allocate half of our brains to vision, it must be extremely useful, right? We only get one brain. If we're going to allocate half of it to vision, that must be a really useful thing. Of course, we don't need neuroscience to tell us that. Just try getting through your day with your eyes closed, and you very quickly realize the thousands of things that vision enables us to do. So keep this in mind. Vision occupies half the human brain. Because of that, or from that, I think we can infer it's computationally hard, and it's really valuable to humans. The same things apply in artificial vision, in embedded vision. It's computationally hard, and it brings a lot of value to systems. Please raise your hand at any point if you have questions, or just shout out. I have low expectations in this regard. The only place I've ever given a presentation and gotten fewer questions than an ECS class is in Finland, where apparently it's a cultural thing. You just don't ask questions. I don't know. So we use this term, embedded vision, simply to mean the practical, deployable form of computer vision. Computer vision is a term that has a lot of baggage from 50 years of research and kind of niche, exotic deployments in things like high-end manufacturing and military applications. So we've chosen the term embedded vision to mean the practical, deployable sort of successor to computer vision, if you will. What's making this transition happen right now? Why didn't it happen 10 years ago or 10 years in the future? Well, it's because the technology's crossed important thresholds. Remember, from neuroscience, we get the inference that vision is computationally demanding, and this is true for human vision and also for embedded vision. It takes a lot of processing power, typically in the order of tens of billions of operations per second, to do vision. It's easy to see why this is so. It's simply the product of the data rate and the amount of computation being applied to that data. Vision, of course, is operating, at least in most interesting cases, on video data. 30 frames per second, 60 frames per second, VGA, 720p, 1080, and so on. That's just a lot of data. Tens, hundreds of millions of data elements per second. Now comes the question, well, what are we doing to that data? Even something really simple like correcting for the geometric distortion of an imperfect lens typically could require, let's just say on the order of 10 operations, not just per pixel, but per color component of a pixel in the image. So, 10 operations per element times 100 million elements per second. We're already up to 1 billion operations a second of compute power, and we haven't even done anything interesting yet. So it's very easy to see how we quickly get up into the tens of billions of operations per second. Now, if you're doing the DARPA Grand Challenge and you have the whole cargo area of an SUV in which to install racks of servers with high-end CPUs and GPUs, this is no problem, right? Tens of billions of operations per second, that's easy. If, on the other hand, you're trying to build a small product, a low-power product like this pen, which incorporates vision, then it's an entirely different matter. Right? To fit billions of operations, tens of billions of operations per second into something small, inexpensive, this is a $100 product, and low power, this will run for many hours on whatever small battery they can cram in here, that's hard. And that's why vision is just taking off now, because we're just getting to the point where processors with enough processing power, but low enough power consumption and cost for vision applications are becoming widely available. And the same can be applied to image sensors. Thanks largely to smartphones, image sensors have become an enormously high-volume market with a huge emphasis on small size, low power, and low cost. So not only have the processors crossed an important threshold, but so have the image sensors. Here's quantitatively one view of the processors crossing the threshold. Now, there are many classes of embedded processors, as I'm sure you know. One class is DSPs, digital signal processors, and I chose those here because classically DSPs are really optimized for a sweet spot of, yes, we need high performance for streaming data, algorithmic intensive kinds of workloads, but we also need it at low power and low cost. So I chose a very mainstream DSP family from Texas Instruments, the C6000 family, the single core version of that. And I looked at how the performance of that family has evolved over the last 20 years. And using the very simplified metric of billions of multiply accumulate operations per second, which is kind of the equivalent of MIPS for digital signal processing, what you can see is that just in the last few years, these processors have crossed this threshold of 10 billion operations per second, which is a kind of typical workload, typical performance load for an embedded vision application. Some are much higher, some are much lower, but order of magnitude, 10 billion operations per second is typical. And we've just gotten to the point in the last few years when you can get a processor not for 100 watts and $500, but for a watt or two and $10 or $20 that will deliver this kind of performance. So that's what makes it possible now to put vision in everything. But as my mother used to tell me frequently, perhaps you've heard this, just because you can do something doesn't mean you should. So this is we can, but why should we put vision in things? Well, just like vision provides incredible versatility and utility for humans, it provides incredible versatility and utility for machines. It can, fundamentally what it does, I think, is it upgrades what machines know about the environment. So if you're interested in how machines interact with the physical world, and I would contend that that's really the only interesting kind of machine, is machines that interact with the physical world. Machines learn much more about the physical world from vision than almost any other way, which is also true for humans. And with that additional awareness of what's going on in the physical world, they can achieve a lot of things. They can be safer. They can be easier to use. Interacting with humans in a way that's more natural to humans, for example. They can be more insightful, being able to determine things about what's going on in the environment, like a person's emotional state, for example, that are difficult to or impossible to determine in other ways. So vision, just like it brings huge amounts of information and functionality, if you will, to humans, brings enormous amounts of information about the physical world to machines, which enables many, many new kinds of functionality. I'm going to show you a video here. Let's see if the sound will work. This is, I have dozens of these, and I've just chosen 3 to show you today. I'll give you links in the slides to more if you're interested. But these are a few, I think, very innovative products that are entirely enabled by vision and that hopefully give you a sense of what I'm talking about when I say vision brings entirely new kinds of functionality to machines. This first product is from a company called Orcam, based in Israel. And what it is an aid for people who are severely visually impaired. Not completely blind, but severely visually impaired. And you'll see in this video how it works. The camera clips onto the earpiece of regular eyeglasses. There's an earphone and a pocket computer roughly the size of a smartphone. And one of the really innovative things about this device you may have noticed is it uses a person's finger like a mouse to direct the focus of the vision system. So I'm interested in this thing. What is this piece of currency in my hand? What is this street sign? What is this text on this menu? And then gives a spoken interpretation, either text-to-speech or object recognition of what is that thing that you're pointing at. This was just announced last week. Does anybody have or has anybody seen a Roomba robot vacuum? So that was cool when it debuted. What was that, 10, 15 years ago? But it's a pretty clumsy thing, right? You see it work its way through a room. It's constantly bumping into things because that's the only way it finds things, is bumps into them. And also winds up missing spots and going over some spots many times because why? It has no model. It has no model of the space. It's just blundering around in a very kind of brute force way, bumping into things. Oops, can't go there. Let's try over here. This is a successor to Roomba. This is a Dyson product that was just announced. And not surprisingly, it uses embedded vision to solve this problem. Not just in a straightforward way that you might think of looking around, but actually using 3D vision to in real time create a 3D map of the room and everything in it, at least at floor level. Now it has a model of the space. Now it can map out a path through the space that never collides with anything in the space and covers each patch of floor once and exactly once. Vastly more efficient approach, but only possible really with vision or some comparable sensing technology. You may say, well, that's not so impressive. I've seen things like this before, and you're right. For example, when they land the Mars rovers on Mars, one of the ways that they avoid having them land upside down in a crater is they use 3D vision to look at the surface, compare what they see to a stored map, and then navigate, maneuver the landing vehicle so it lands in an appropriate location. Again, just like I said earlier with the DARPA Grand Challenge, this isn't hard if your budget is hundreds of millions of dollars for the actual product you're building, right? But if your budget is a few $100s for a consumer product, that's where it gets really challenging. Think about the computational complexity of doing this 3D map construction in real time on then think about mapping that onto a very low cost and a low power processor. That's where some of the very interesting challenges arise. Here's one more example. Also very small, low power, vision-enabled product. What this device does is turns any surface into a touch screen using 3D vision. Yeah. Again, it's not so much that you can do this that's interesting, it's that you can do it in a very small, low-cost, low-power device. This device is from a company called Ractive, as in R Active without the E on the end, based in Singapore. They've just started initial production of this device. The retail price is $75. I've got a bunch more very cool example videos here. I'll make the slides available, and I encourage you to check these out to see more about how people are using this kind of technology for real commercial applications, not just sort of science fair, do it because we can. Yes? So that's a great question, processor specs. I'm going to come to, I have a section on processors coming up, so let me see if I answer that question there. So how does this work, first of all, from kind of a behavioral, from an algorithmic point of view? This is, of course, a whole rich field, computer vision. I'm going to give it an extremely superficial treatment here, just so those of you who haven't had exposure to computer vision get some flavor for what's going on algorithmically, and then we'll get into the implementation challenges, processors especially. So, of course, you start by acquiring images. Typically, you then need to optimize the image or enhance the image because the images are often imperfect, especially in a product that needs to work kind of out in the wild. There are applications like factory automation where imaging conditions can be very tightly controlled. For example, imagine a bottling plant where beer bottles are coming down a conveyor belt, and the job of the vision system is to make sure that each beer bottle is filled to the appropriate level, has a cap affixed, and has the label affixed. Well, what we can do in a case like that is we can make sure there's nothing in the background that's going to make the problem harder. We can make a really simple, plain background. We can have optimal lighting from the same vantage point as the camera. We can locate the camera in exactly the optimal position to get the best quality image. And that's what they do in factories, and it works great. But out in the real world, if we're talking about a robot vacuum or a device that's a PC peripheral or an automotive safety device, it's quite the opposite. We have no control over the imaging conditions, and they're often atrocious. We have bad weather, we have glare, we have dirty lenses, we have just limited light available. Things are moving very quickly. So a lot of the first steps that happen in a typical vision system in the wild is doing the best we can to improve the image. Now, of course, cameras do this, but they are optimizing for different criteria. They're optimizing for a pleasing looking image that we're going to look at and say, yes, we like how that looks. For vision, we're optimizing for different criteria. We're optimizing for maximum information, in some sense of the word information, in the image. Once we've gone through those steps, which include things like contrast enhancement, noise reduction, color correction, lens distortion correction, then we move to extracting information from the image, converting pixels into objects, if you will, and then reasoning about the objects. For example, is this person that I find in this location in this frame, is that the same person that was in this nearby location in the previous frame, and can I therefore infer that there's a person moving on a certain trajectory? So that's a very high-level view. I'll go into a little bit more detail, but one of the really important points here is that as we move through this pipeline from the image sensor, and of course there may be several image sensors. It doesn't necessarily have to be just one. A lot of products use 2, 3, 4, or more image sensors depending on what they're trying to do. But for purposes of simplicity, let's just say there's one. Moving from the image sensor through all of the algorithmic steps to a point where some decision can be made, we go through a cascade, a feed-forward pipeline of steps, starting with image improvement, then typically looking at small, low-level features in the image that may, when they're collected together, help us identify an object. For example, corners on that may indicate features of a face, like a mouth, eyes, and nose. Then we start aggregating those small features into larger objects and eventually reasoning about those objects. Is that really a person or is it a sign? Is it the same person that I saw at this nearby location in the previous frame? And so on. A couple of really interesting things here. One is that as you go from the left side to the right side of the pipeline, the data rates go down quite quickly because we move from, at the front end, operations that touch every pixel or every color component of every pixel, so massive amounts of data, to, in the back end, algorithms that are talking about objects like people, where there may only be a few such objects in a frame. So we go from hundreds of millions of pixels per frame to perhaps just a few objects per frame at the end of the pipeline. So the data rates go throughout this pipeline go down by orders and orders of magnitude. And of course, as data rates go down, computation load tends to go down, except that there's a counteracting force happening here, which is that the complexity of the algorithms goes up very fast as we move through these stages in the pipeline. In the front end, when we're doing things like color correction and lens distortion correction, the algorithms tend to be very simple algebraic transformations, things like filters, for example. But then as we get to the middle and the end of the pipeline, where we're really reasoning about, well, is this collection of corners a face? The algorithms are much, much more complex. And so we go from tens of lines of code, for example, in the case of lens distortion correction, to potentially tens of thousands or even hundreds of thousands of lines of code as we get into some of these heuristics in the back end reasoning about objects. So data rates are going down as we move through the pipeline, but algorithmic complexity is going up. And so computation requirements tend to be substantial at each stage of the pipeline because the computation requirements are the product of these two things, like we said earlier. Also, the data types tend to change. At the front end, we have pixels. They're usually 8-bit integer quantities or something like that. But as we move through these increasingly complex algorithms, often we wind up with more complex data types. For example, when we talk about applications that are doing things like 3D, mapping 3D spaces, floating point is a virtual necessity. So there's a lot of heterogeneity in the computation, even within one vision application. From the front end through the pipeline, different data rates, very different data rates over many orders of magnitude, different algorithm complexity, different data types. And this is one of the things that makes it a challenge for processors, because it's easy to find a processor that's good at one thing. It's hard to find a processor that's good at a wide diversity of things, and good in the sense of extreme cost efficiency and energy efficiency. Now, the view I gave you a minute ago is very simplified. In reality, the algorithms wind up being much more complex. And one of the reasons for this has to do with models or the lack of models. In other fields in sort of applied electrical engineering, for example, wireless communications, we have really good models of the physical world, really good mathematical models that predict quite well how, for example, wireless signals propagate through space, reflect off objects, are absorbed, and so on. And so what this means is that we have a really good foundation for reasoning about the design of a communication system under a known set of constraints and goals. If we have a known set of constraints and goals, experts in wireless system design tend to converge on similar answers in terms of what should this system look like. Should it be CDMA? Should it be MIMO? And so on, because they're guided by these strong mathematical models. In vision, there really are no such models. And what that means is that vision is a fundamentally experimental field where we try things. We try things in the lab with a limited amount of data that we have on hand. We think they work. We take them out in the field. They break. We diagnose why they broke. We bring that data back to the lab. We refine our algorithms, and we repeat that cycle essentially forever. And we wind up with algorithms that look like this. Very complex, lots of feedback, lots of concurrency, lots of heterogeneity in terms of data types, data rates, algorithm types, and so on. So lack of models is a key challenge. I'm sorry, question?
Can you give a short example of such a case where the object recognition has to do some modified filters, pixel processing?
The kind of feedback, an example of this kind of feedback path. I'm trying to recollect from a really good presentation on this topic, which I can point you to later, that I saw about a year ago. But a good example might be this. You have, in automotive applications, for example, we have cameras that are doing a whole bunch of things, including they're looking for lane markings on the road. And as you know, those can be hard to see depending on the imaging conditions. And glare and lighting and how worn they are and the angle of the light and so on. And so one of the places where you might see a loop like this is the back end, or the middle end really in this case, might say, look, I'm having a really hard, I see the road, but I'm having a really hard time finding the markings. It might then ask the front end to change some of the settings, right? Turn down the gain, compress the dynamic range, do something to give me a better shot. This isn't working for me, right? Can you adjust the image because under these conditions I'm not getting something I can work with? That's kind of a simplistic example, and I don't know how realistic it is, but at least it illustrates the concept. So these difficult imaging conditions are a key reason why vision is hard. I mentioned that earlier. Lack of analytical models is a key reason why vision is hard. Another reason why vision is hard is that there's an enormous design space before we even get to implementation. Just when we're at the functional level of MATLAB or C++ code or whatever, prototyping algorithms, there's an enormous number of knobs we can turn on these algorithms. And that creates a huge design space where it's really hard to find what is the optimal set of settings for this set of algorithms, for this set of conditions. And actually, there's some very interesting work that's recently been done in a DARPA program called Visual Media Reasoning, where they've developed some tools to help in the automated exploration of this design space. Once you have an algorithm or a small set of algorithms and a set of parameters and then a set of data, images, and what we call ground truth, meaning what's the reality about those images that our system should be extracting, an automated way, a framework to help with automated testing and exploring that design space to help you figure out what the best parameter settings are. It's also true that vision systems are challenging because it's a very much multidisciplinary problem. You have optics, you often have lighting, you have image sensors, you have algorithms, you have processors, you probably have networking of some sort, databases, and so on. And even within big, sophisticated organizations, it's rare to find one group of people that has all of the necessary expertise to optimize across all of those domains. But it really does require co-optimization across all those domains to get an optimal system design. You know, if you've got the wrong lens, no amount of optimizing the image sensor or the image enhancement algorithms is going to offset that bad lens selection, for example. So those are some of the things that are challenging, make it challenging kind of at an algorithmic functional level. There's a whole other set of challenges we get into when it comes time to implementation. Once we get to the point where we say, okay, we have the algorithms we want, now we're going to implement them on some kind of embedded processor so that we can actually deploy them in a product. The first challenge, as I mentioned earlier, is simply there's a lot of performance required relative to what's typical in embedded processors. We need that performance. We need it at very low cost, very low power consumption in most cases. Now, in electronic system design, a classic way of solving this problem of needing a lot of computation in a low amount of power consumption and cost is to put the algorithms into fixed function hardware, right? To design specialized logic that implements the algorithm. For example, if you pry open your set-top box or your nice laptop and you dig down into the bowels of it to find the piece of silicon that's actually doing H.264 decode, even though you have billions of operations per second of compute power in your CPU and your GPU, they're not doing H.264 decode. There's like 1 square millimeter of silicon that is doing H.264 decode, and that's all it does. And it can't do anything else. Because it only does H.264 decode, it's amazingly efficient. And it does that H.264 decode for almost no money and almost no power. That approach, unfortunately, doesn't work well in typical vision applications because the algorithms tend to change very fast. Why do the algorithms change? It's primarily 2 reasons. One, I already said, which is we don't have analytical models. And so in the absence of analytical models, we experiment. Lots of people experiment, and they constantly come up with new and better approaches, try and outdo each other. Number 2, we don't have standards in vision the way we have in multimedia and wireless. In wireless, we have to have standards, right? If my smartphone can't talk to your base station, there's no wireless industry. So standards are essential to wireless communications. They're not essential to vision, however, because vision systems generally do not talk to each other. They don't interoperate with each other. They're standalone in that sense. And so vision systems are not influenced by the same standards in the same way that things like wireless and consumer multimedia and broadcast are. So given the experimental nature and the lack of standards, we wind up with algorithms changing very, very fast, which means if you burn your algorithms into gates, by the time you're done with the verification and tape out the chip, the algorithm's changed. So we need high performance. We need it at low power and low cost, but we also need it to be programmable so that we can update the algorithms as our ideas change about what algorithms we should be using. Yes? Yeah, I mean, I'm somewhat overstating the case for effect, and I'm saying probably even before you finished your design, you'd find that your hardware was obsolete because the guys in the other room working on the algorithms would go, oh, we can do this much better if only we change the algorithms this way. And you'd go, just shoot me because I just spent the last 9 months optimizing this down at the gate level. I can't change it now. Now, in reality, there's a continuum, and often what happens is the front-end steps, things like the image enhancement and 3D stereo depth extraction, which are relatively simple and relatively stable algorithms that people have been using for decades, can and are reduced to fixed function hardware. And later stages, which are less stable, is where it's dangerous to put things into hardware because the algorithms keep changing. And so people rarely do put them into hardware. Yes?
What about consumer products like Roomba or what they keep updating the firmware?
It's not so much that so let's say the Roomba, the Dyson robot, they deploy it in the field. I'm not necessarily talking about upgrading your unit once it's in your house, but I'm talking about next year's model and next year's model. Doing a custom chip is enormously expensive, time-consuming, and risky. So people do it only when they have to, and only when hopefully their requirements are really stable. So more likely, every 6 months, Dyson's going to have a new version of the robot with better firmware, better navigation. Maybe you'll upgrade yours, maybe you won't. But the point is, if they did a fixed function chip that was based on today's algorithm, they might not be able to upgrade it then in 6 months when they have a slightly better or maybe a much better algorithm. So I'll come back to processors, but key point here is, since we can't do custom hardware, we have to use a programmable processor. CPUs are the programmable processors, the default programmable processors that get used in everything, general-purpose processors. But general-purpose processors are pretty inefficient when it comes to performance per watt and performance per dollar, often way too inefficient for these kinds of applications. And so what usually happens is we wind up using some sort of heterogeneous collection of processing elements, including a CPU, but then one or more other kinds of processing engines. And that's how we get the efficiency that we need with the performance that we need. But heterogeneous processors are complicated. They're complicated to program. They're complicated to debug. And so that adds another layer of complexity to implementing these systems. There'll be more about processors in a minute. Question? How far are we from DSPs that are tailored to embedded vision? That's a great question. They're out today. Yeah. They're not sort of widely publicized, but there are quite a few companies making them, and I have a slide on that coming up. What time are we supposed to finish here? Is it 12:20 or 12:30? 12:30? Okay. I'll try not to push it to the very last minute. Just want to pace myself here. Okay. So let's look at a real example. You may have started to see cars now are starting to come equipped with vision-based safety systems. The industry acronym for this is ADAS, A-D-A-S, which stands for Automated Driver Assistance System. And these systems have a variety of functions that they perform. The most common is what, again, in the kind of industry tortured lingo, they call forward collision avoidance. What that means is helping you not crash into things. That's the most common functionality. So one or more cameras looking out typically through the windshield. They're typically mounted up by the rear view mirror. So they have a similar view of the scene as the driver. And they're looking at what's happening, initially specifically for other vehicles that you're driving behind, and looking for a situation where you are closing too fast on the vehicle in front. And when they detect that situation, if it's a passive system, it's going to warn you with a shrieking alarm, perhaps. If it's an active system, it'll start by warning you, and then if you don't seem to be getting with the program, it will stop the car itself by applying the brakes. So that's one function that these ADAS systems provide. But very rapidly, they're providing lots and lots of other kinds of functions as well. I mentioned sign reading. So some of them will read speed limit signs and warn you if you're speeding. Lane departure warning is another common function. I mentioned this earlier, where cameras either behind the front mirror, the rear view mirror, behind the windshield, or in the side mirrors looking kind of forward and downward, will look for the lane markings in the road. And if you seem to be drifting out of your lane unintentionally, in other words, you didn't make a deliberate kind of steering input, you didn't use your turn signal, you just seem to be kind of wandering out of your lane, the system will warn you. Or again, if it's an active system, it'll provide steering input to correct the situation and keep you in your lane. There are many other functions that these systems are providing, and some of the videos that I'll give you links to illustrate these. Some of them are inside the car, for example, looking at the driver to see, is the driver getting sleepy? And if so, warn the driver, hey, maybe you want to take a break now. But let's stick with the lane departure warning, and let's just take a high-level look at how that might work from a vision point of view. Not surprisingly, when we're looking for lane markings, really what we're looking for is edges in images, right? We're looking for high contrast features with certain geometric properties. That's what lane markings, are. And so often the first step in a lane, or after we do some of the image improvement, the first step of extracting meaning is an edge detection algorithm, which might take you from something that looks like this to something that looks like this, from a natural image to an edge image, where the black pixels are highlighting edges in the original image. And this is computationally very simple. There's an algorithm invented by a Berkeley CS professor, John Canny, called Canny edge detection, which is kind of the classical approach to this, which is essentially 2D FIR filtering. So from a writing code point of view, just maybe a dozen lines of code. But since you're applying it across the entire image, and then 30 frames per second, or maybe higher, because keep in mind, we have a moving vehicle here, so we need lots of images per second to keep track of what's happening, the computation becomes significant. The edges produced by something like Canny edge detection are not going to be ideal edges like you might draw if you were drawing the scene, though. They're going to be kind of noisy and messy because the image data from the real world is noisy and messy. And to help us figure out what we're really seeing, help the algorithms figure out what they're really seeing and what's really a lane marking and what isn't, often we'll take a step where we simplify and clean up those edges. Edge thinning, kind of binary morphological operation, where we look at a local neighborhood of pixels and remove some that are sort of unnecessary to the fundamental edge that we think we're looking at. So now we have a cleaned up edge image. Now the question is, are there lines represented by these edges? Because lane markings are lines, right? These edges could be any pattern. They could be a sine wave. They could be a circle. We're looking for edges. A classical technique for extracting lines from an edge image is called the Hough transform. It actually can be used to extract other shapes as well, like circles. In this case, we're using the Hough transform. We're applying the Hough transform, which is a kind of histogramming technique. It finds each edge pixel, and it looks at the neighboring edge pixels, and it starts to build a histogram of essentially all possible lines in the image. And if a possible line has a lot of actual edge pixels on it, then it likely is a line, right? So it's kind of a voting technique. Very simple to describe and write in code, but very computationally demanding. Now, for lane markings, we're probably looking for, at least initially, straight lines. And so this is a place where that earlier step of correcting the geometric distortion from imperfect optics, imperfect lenses, is important, because that geometric distortion will make straight lines look curved and curved lines look straight. And so if those kinds of properties are important, then it's important that we do that lens distortion correction step up front. This is a little more detail on the Hough transform, but I've already pretty much described that. And then typically we're going to start applying additional heuristics to determine, well, of all these lines in the image, which ones are likely to be lane markings. Well, we know some things a priori, right? Like we know lane markings don't usually appear in the sky, so we're probably going to discard images that are in the field of view well above the roadway. We may also reason based on color. Now, at this point, we only have a binary image based on a grayscale version of our original image, but we could still retain the color data from the original image. And once we have candidate lines, we could refer back to that color data and say, well, this line here, what color was it in the original image? If it was white or yellow, maybe that gives it a higher probability of being a lane marking. If it was black, maybe that gives it a lower probability, and so on. Often then we're also going to do tracking of these candidate lane markings from frame to frame. Now, of course, the markings themselves are not moving from frame to frame, but the vehicle is moving. So there's relative motion between the lane markings and the car. And so by tracking a candidate lane marking from frame to frame, we can get some useful information. For example, maybe the imaging conditions are marginal, and so every third frame we don't get a clear edge on a particular marking. Well, it's not helpful to us if we're oscillating back and forth between it's a lane marking, it's not a lane marking, it's a lane marking, it's not a lane marking. We got to decide. And one way we can decide is look over time and say, well, in this frame it was here, in this frame it's here, in this frame it's here, here it's missing, but it's back in this frame. Yeah, I think it's a lane marking, for example. We can also predict where the car is moving relative to the lane marking. So, for example, in the lane departure warning system, we don't want to wait till the car has exited its lane. We want to anticipate when it's about to exit its lane and warn the driver or take corrective action at that point. And so things like Kalman filters are very helpful for doing this kind of tracking and prediction. We're at a stage now where we're operating on much lower rate data. Now we're only looking at the lines that are good candidates to be lane markings, and so instead of millions of pixels per frame, now we're probably down to dozens of candidate lines per frame. So the data rate's much, much lower, but the algorithms are starting to get more complex. So hopefully this gives you a little bit of a flavor of how this kind of application might work. This is kind of the textbook version. This is what you might start with. Then you take it out in the field and you start testing it over thousands and thousands of actual road miles under varied weather and lighting conditions, and you find that it failed in various situations. You'd capture that video and you'd bring it back to the lab and you'd iterate and improve the algorithm. And this happens essentially continuously. Has anyone heard of the company called Mobileye? Mobileye is an Israeli company that just was in the press a couple weeks ago for having a phenomenally successful IPO. They are really the pioneer and the leader in this vision-based automotive safety technology, and they've invested something like 1,000 man-years in their algorithm development so far. And there's no end in sight, right? They're gonna keep working on this because it's never perfect, and it's never going to be perfect. But as processors become more powerful, algorithms become more sophisticated, they can get closer and closer to perfect. Okay, so a little bit about processors now. I mentioned that high-performance CPUs, I'm not talking about microcontrollers here, but x86, ARM Cortex-A9, this class of processor, they often have sufficient processing power for vision applications, especially when you bring in the single instruction multiple data capabilities like SSE and Neon. But when you start running them at 2-3 gigahertz and you 4 or 8 cores per chip and maxing out the SIMD lanes, they start to get very warm and also expensive. And you can see that with a mobile phone. If you take a typical smartphone today that's got 2 to 3 gigahertz ARM Cortex-A15 type cores, and you just max them out, it can't run in that state very long. It starts to get too hot, and thermal limiting comes into effect and forces the CPU clock speed to go down so the phone doesn't melt. So this obviously isn't going to work for a lot of applications. It isn't a very energy efficient, it isn't a very cost-effective way to get the necessary performance. So like I mentioned earlier, a very common approach is to use heterogeneous processing. Use a CPU plus one or more specialized parallel processing engines that are still programmable, but that are more specialized and can do the highly data parallel algorithms that are common in these applications at very low cost and energy consumption. And ideally, what you hope to achieve is the best of both worlds. These more specialized processors are harder to program than a general-purpose CPU. You have to know more, and you have to work harder to get an efficient implementation on these specialized architectures. But you get a more efficient implementation by doing so. So in the ideal world, 80% of your code is only consuming 20% of your processing cycles, roughly, and that can stay on the CPU because it's only consuming 20% of the processing cycles. And so you can keep that 80% of the code on the CPU where life is good in terms of ease of programming and really good tools. Then the 20% that's really doing the computational heavy lifting, that is the 20% of the code that you take and you put on the more specialized processing engines, and it's going to be more effort and more skill required to do that, but you're going to get an enormous gain in efficiency, performance per watt, performance per square millimeter of silicon by doing so. And so virtually every implementation that you see kind of in the wild today of computer vision, embedded vision, is using some form of heterogeneous processing. And there are many different forms of heterogeneous processing. Mobile phone application processors are a great example. There are many, many processors besides the general purpose CPU in the typical mobile phone application processor. GPU, DSP, ISP, which is the image signal processor. And that's by necessity because the phones are extremely constrained in power consumption and also cost. So if you're trying to do some sophisticated computer vision on a mobile phone or tablet, and it's something that's going to run for more than a few minutes at a time, so you care about the energy efficiency, you almost certainly have to get it off the CPU and find a way to put the heavy lifting onto the GPU, the DSP, or one of the other more specialized but more efficient processing engines. And this is not true only in mobile phones, because these mobile application processors are now starting to find their way into lots of other applications, like automotive systems, for example. So these almost exact same processors that you find in smartphones are now showing up in lots of other places. General purpose GPU, this is the concept of taking the graphics processing units, which were originally designed, of course, for doing 3D graphics rendering, and using their very powerful parallel architectures to do other things. Now, this idea has been in common use in PCs and servers and supercomputers for at least a decade, but it's just now, and I mean literally right now, starting to be used in things like mobile phones and embedded systems. NVIDIA recently announced this new Tegra K1 chip, for example, for embedded applications, and they're really focusing on using the GPU to offload things like vision functions from the CPU with much lower energy efficiency. This is getting easier now with non-proprietary programming languages like OpenCL that enable you to program the GPU in a way that's not specific to that GPU supplier. NVIDIA really pioneered this approach. Their version of it is branded CUDA, but NVIDIA has their proprietary programming language. And so you can't take that code from an NVIDIA GPU and move it over to an AMD GPU or an Imagination Technologies GPU that's in your iPhone or something like that. With OpenCL, you have the ability to move from GPU to GPU, and not only on GPUs, but move to FPGAs, DSPs, and other kinds of sort of data parallel processing-oriented architectures. So more and more attention is going into using GPUs for these applications now. You asked a few minutes ago about DSPs optimized for vision. And in fact, there are roughly 8 or 10 products out there that are DSP processors, but really tuned for vision applications. Most of them are not chips. Most of them are silicon intellectual property cores, the same business model that ARM uses, where they don't make the chips. They provide the processor design to chip manufacturers, who then implement that processor on their SoC alongside whatever other processors and buses and memory, et cetera, they need for their application. So I've listed a few of those companies here: Siva, Cognivue, Vidiantis, Tensilica, which is recently acquired by Cadence, Apical. These are all companies that offer vision-specific programmable DSP cores, although they may not call them that, in the form of licensable silicon intellectual property cores. There are very few companies that offer these kinds of processors at the chip level. In fact, I think the only one doing that really today that's not totally market-specific is a company called Movidius. If you saw the Google Project Tango, if you haven't seen it, check it out. They have a smartphone prototype that integrates 3D vision, so you can do things like mapping interior spaces, similar to what that Dyson robot vacuum is doing. They use the Movidius processor in their Project Tango smartphone prototypes. Also, FPGAs are starting to be used as compute engines in these kinds of applications, and that's becoming more feasible now that there are ways to implement algorithms on FPGAs that don't require going down to doing register transfer level hardware design in Verilog or VHDL. For example, high-level synthesis tools that allow you to take algorithms expressed in C or C++ or System C and synthesize RTL, or OpenCL, like I mentioned a minute ago. Altera, for example, has an OpenCL to FPGA flow that they've been using in the high-performance computing space for servers, and that they're now bringing into the embedded space as well. So those are a few of the common processing options. If you're interested in more about kind of practical computer vision and what kinds of processors and tools are available, what kinds of applications are people implementing, I want to invite you to come to our website. The Embedded Vision Alliance is an industry organization that I started about 3 years ago to help facilitate the widespread use of computer vision technology in products in industry. And the Alliance's main mission is to provide practical technical education to engineers in industry who want to understand how they can use this technology in their products. So you'll find lots of good video presentations and tutorial articles and code examples and so on the Alliance website. I've got a postcard here about it if you're interested in learning more about the Alliance. All those resources are free to anybody who wants them. You can also meet our member companies. There are currently 42 member companies in the Embedded Vision Alliance that you can find out about on the site. And if you're interested in a job in this space, many of these companies are interested in hiring people to develop the enabling technology and the applications in this embedded vision space. My own company is BDTI on here in the center middle column, and we specialize in performance optimization. So a lot of times end product companies like a Dyson, for example, will come to us and say, well, we have this big pile of MATLAB code, we have this $10 processor, how do we get this functionality into this small, low-power, inexpensive processor? That's what we do for a living. Let's see. If you're really into this stuff, I have this book here that was recently published called Computer Vision Metrics, which is not a typical kind of academic textbook. It's a really practical treatment focusing on feature detectors and feature descriptors, which is a kind of core topic in vision from a practical point of view, including implementation aspects. It's available free in electronic form as a PDF. You can find that on the Alliance website. If you're interested in a hard copy, I have a few that I'd be happy to give you in exchange for you writing a brief review about the book and posting it on the Alliance website. So anyone who's interested in that, come see me after the lecture or send me an email, and I'll be happy to mail you a copy of the book. All right, I think I have time for a few questions. Any questions? Yes?
How did you get into that?
So I'm a digital signal processing guy, and particularly my focus in my career has been the efficient implementation of digital signal processing. And digital signal processing, as you know, is used in a lot of things. It's used in wireless communications, it's used in audio, et cetera. About 5 years ago, my consulting company clients started to bring us our first computer vision projects with these kinds of problems, like how do we fit all this compute into this small budget? And because we also do a lot of work in evaluating processors, we realized over the course of about a year that the processors were just getting to the point where it was going to start to become possible to implement vision in just about everything. And we made the decision at that point to focus our business in this sector. And so we've been hiring people and building up our own skills, and over the past 3 or 4 years doing more and more projects solving these kinds of performance optimization and processor selection problems for mostly electronic systems companies. Any other questions? Great. Well, I really appreciate your time and attention. Feel free to come up and have a look at the book if you want. Grab the postcard about the Embedded Vision Alliance. If you want to see how this $100 pen-sized computer vision product works, I'll be happy to give you a demo.